Hello everyone, I'm Nicolas from FACCTs, and on my behalf as well, welcome to the ORCA 6.1 release event. In this presentation, I will introduce a new feature we added to ORCA for defining fragments. In previous talk, we already seen some examples of fragment usage. For instance, in energy decomposition analysis presented by Dr. Giovanni Bistoni, and in quantum system definition for QM and M schemes showed by Dr. Christoph Ripley. From an ORCA perspective, a fragment is simply a subgroup of atoms of your molecular geometry. We can use fragments for various purposes, such as defining basis set and effective core potentials, performing population analysis, applying constraints, or rigid body condition in geometry optimization, inducing energy decomposition analysis, and defining regions in multi-level calculation. Previous ORCA versions offered two ways to define fragments. The first method was placing a fragment number between round brackets next to the atom symbol in the coordinate definition. For example, in this case, assigning a copper atom to fragment 1 and the 4 ligands to fragment 2. This creates a fragment division reported in the output used to make a spin and charge population analysis. A completely equivalent method was to use a coordinate block, again specifying the fragment numbers between round brackets next to the atomic symbol. Note that these two methods require to define the geometry of your system in the ORCA input file. So, in ORCA 6.1, we introduce a new fragment block that simplifies fragment definitions. The first and most basic usage of this fragment block is by including a definition in which you can manually list the atoms belonging to each fragment directly. For example, to assign atoms 1 to 4 to fragment 2, you can just use a colon to define a range, which means there's no need to list each individual atom. This also works using geometries which are reading from external files. However, the fragmentation block additionally provides several other options for fragmentation, using automatically detection procedures based on bond recognition and graph methods. In this first basic example, containing just one water molecule and one propane molecule, the fragmentation procedure water automatically detects a water molecule in your geometry and assigns it to a fragment. Then, the functional group procedure recognizes and assigns several organic groups, in this case, 2 methyl groups and 1 methylene group, splitting the propane molecule, in this case, into 3 fragments, resulting in the assignation of this case in 4 fragments, 1 water molecule, 2 methyls, and 1 methylene group. ORCA 6 provides multiple fragmentation libraries which may automatically assign fragments in complex systems. So let's briefly review the most important. So the first one is the connectivity procedure. This procedure splits the system into molecular fragments based only in covalent bonding pattern. So this means essentially we assign one molecule per fragment. So this method may be already familiar to the energy decomposition community, as it was traditionally used to automatically assign atoms to fragments when the manual definitions were incomplete. So in ORCA 6.1, this procedure has been significantly optimized for speed while maintaining the same core functionality. The functional group procedure, as already mentioned in the first example, detects defined organic structures like phenol groups, acid groups, amines, and so on and so forth, and assign each one to a separate fragment. In the case of biological systems, ORCA includes several libraries to handle different fragmentation requirements. For the current ORCA libraries, you can assign amino acid residues to fragments. You can also assign the sign change of the amino acid, or there is also a fine-grained version of the sign change especially designed for QML purposes when single carbon-carbon bonds are split between fragments. Additionally, there are three procedures available for detecting and assigning the protein backbone. One which assigns the backbone of each amino acid to a separate fragment, a second one which preserves the peptide bond inside the fragment definition, and a third one which assigns the whole protein backbone into a single fragment. Similarly, for nucleic acids, it is possible to assign each nucleotide in a DNA or an RNA chain to its own fragment, or to assign only the side chain. For the backbone part, there are three options in this case, according to how you want to treat the phosphate. One version assigns the phosphate to the 3' side of the sugar, another version assigns the phosphate to the 5' side of the sugar, and there is a third version which put the phosphate groups in a separate fragments. So in the next talk, Dr. Bernardo de Souza will demonstrate how automatic fragmentation can be used to improve geometry optimization. So just keep these ideas in mind for next talk. So, and finally, among the ORCA internal libraries, we also include two procedures for solvents. The first one, solvents, detects a wide range of common solvents, while the second one, which is called water, only detects water molecules. This second one is more efficient when the only solvent which needs to be detected is of water. All the internal libraries cover many common fragmentation requirements. However, some cases are too complex or too specific to get them included in internal libraries. To handle those, we have implemented an external library procedure which allows you to define your own fragment. For example, imagine we are interested in to fragment this iron-sulfur complex, where we want to assign the two irons and the two sulfur into one fragment, and from the ligand part, we want to assign each benzimidazole ring to one fragment. And there is no internal library which generates this specific fragmentation. You can create your own external library and provide it to the code. So the only thing you need to do is to create your own XYZ file containing the geometry of the iron-sulfur core and one benzimidazole. Then use the external library procedure in the fragmentation block. So what the code is going to do is going to read your geometry, transform it into a graph, and search for it inside your geometry. So in this case, we will first assign the iron and sulfur to a first fragment, and then each of the benzimidazole rings are going to be detected and assigned to a different fragment. Finally, the last elementary procedure I want to present in this section is the extend procedure. So extend has been designed to simplify the fragment definition assignment. So in this case, what extend does is to include into previous fragment definitions oxygens bound to carbon atoms or hydrogens bound to carbon, nitrogen, or oxygen. So suppose, for example, in this case, we define an external library to fragment this glycine molecule, and our external library only contains two carbon atoms and one nitrogen atom. So we use in this case just the external library, and we assign 3 atoms to a fragment. And then to complete them, for using all the hydrogen and the oxygen, we use extend. So extend automatically search which are the bonds, check if those bonds belong to carbon oxygen, hydrogen nitrogen, hydrogen carbon, or hydrogen oxygen, and if that is the case, they include it into the definition of the fragment. So this is very useful in QM cases for assigning protonation state without the requirement of defining all the possible combination of protonation states. So far we have looked at elementary fragmentation tools, but this procedure can also be combined to create powerful fragmentation tools. So in the past examples, I just slightly put a bit of the combination, but let's take a look at how we combine this to do more complex systems. So for example, let's consider the hemoglobin case. And just to simplify a bit the visualization, we can display just the hem groups. We are going to take only the oxygen for the water and a few key side change part of the amino acids. If we want to fragment a system of this size by hand, this is going to take a lot of time and is very error-prone. So what we can do here is to define an external library containing the heme group, then assign the protein backbone, assign the side change, and finally assign the water. And since in this case, the heme fragment can be defined just by extracting one heme group from the original geometry, the entire process becomes very fast and straightforward for the user. And to finish this talk, let me show you one last example, the fragmentation of one in riboswitch or QMM setup Dr. Christoph Rieplinger presented here. This system contains an RNA chain, while a separate guanine molecule simultaneously acts as a ligand. So to define the QM region in this system is necessary to define our fragments by splitting the side change of each nucleic acid. However, we also want to fragment the major part of the bond of the guanine ligand. So note that in this case, this particular type of fragmentation is in principle not possible to be done using just the elementary procedures I showed you before. Because if we try to start and automatically assign of the side change of the nucleic acid, which belongs to the RNA change, the one illegal will also be assigned to a fragment since it shares the same structural features as the one in side change in the RNA change. On the other hand, if we attempt to first detect and assign the small fragments needed to split the ligand, we will unintentionally fragment the side change of the nucleic acid. So to solve these kind of situations, we introduce a new set of procedures, which are the delete procedures. The delete procedures, what exactly done is just remove previously assigned fragments. So the major part of the assignation procedure have got a corresponding deleting procedure. And if we combine them in an appropriate way, we can protect some of the atoms to be assigned by other fragmentation procedures. So take a look, for example, to the procedure used by Christoph to generate the fragment to define the QM region. So first we can use a nucleic acid procedure. This procedure, what does is assign nucleic acid, but they have to be bound to a sugar phosphate backbone. So in this case, the ligand remains unassigned as it does not get any sugar phosphate bond. Then we can apply a functional group procedure which assigns fragments only in the remaining atoms, which in this case belong to the fragment. And as a third step, we delete all the fragments generated in the first step. So after these three steps, we generate the fragments to protect them from the functional groups, then use the functional group to cut all the bonds and generate the fragments only in the ligand, and finally we delete the fragments generated in the first step. And then finally we can just assign the backbone and the side change of the RNA. So the examples I presented today exemplifies some of the advantages of the new automatic fragmentation methods we include, but the new fragmentation section designed in the redesigned manual include more detailed examples and practical guidance to help you to define fragments more effectively. So if you have got any further question, also feel free to post it in the ORCA forum, so we try to help as much as possible. So thank you very much for your attention, and I'm happy to take any questions you got.